Ask an AI to build a payment flow and it will give you a standard REST endpoint. Request, wait, response. But what happens when the NPCI switch takes 6 seconds to respond during a peak hour sale? The connection drops, the app crashes, 10 million users lose their money. This is the network trap. Generating the API is free. Designing the asynchronous payment flow that never drops a transaction is the job. 5 things you will own after this video. The difference between synchronous and asynchronous flows. The polling strategy for clients. The webhooks versus long polling trade-off. The exact state machine every payment requires. And the 5-phase interview framework to design this flow in 45 minutes. Watch this video to the end because understanding asynchronous callbacks is the difference between an app that scales and an app that crashes. Let us build it. Here is the AI default, asynchronous payment request. The client sends a post request to the API gateway and waits. The gateway forwards the request to the bank API and holds the connection open. It waits. Here is the trap. The bank is slow. It takes 30 seconds to respond. The API gateway holds the thread open. Multiply this by 10,000 concurrent users and the server runs out of threads. It crashes. You cannot design a payment system synchronously. Let us trace the correct asynchronous flow. The app initiates the payment with the post request to the payment service. The service immediately drops a payment event into a Kafka queue and returns a 202 accepted response to the app. The connection is closed. No threads are blocked. Background workers consume the Kafka queue at their own pace. If NPCI is slow, only the background workers are delayed. The API remains blazing fast. The worker forwards the actual payment request to NPCI. Because the flow is asynchronous, we need a state machine. Every transaction starts in the initiate state when the API is hit. Once the worker picks it up and forwards it to NPCI, the state transitions to pending. This means the money might have moved, but we do not know yet. When NPCI fires a success webhook back to our server, the state transitions to success. If NPCI fires an error webhook or no webhook arrives within the timeout window, the state transitions to false, either success or false. These are the only terminal states. Here is the architectural judgment AI gets wrong. If you ask an AI how the server should know the payment is done, it defaults to short polling. Just keep asking the bank every second. But at PhonePe scale, polling means billions of wasted requests. You trade the easy implementation of polling for the efficiency of webhooks. The bank pushes the update to you only when the state changes. You have seen every layer and every trade-off. Let us put it all together one final time. The full system in one clean view. Hop 1. The app sends a post request. Hop 2. The API queues the event in Kafka and returns immediately. Hop 3. The worker consumes the event from Kafka. Hop 4. The worker calls the NPCI switch. Hop 5. NPCI processes the transaction and fires a webhook back to PhonePe. Hop 6. Meanwhile, the client app has been safely long polling the API for the final status. You now own the architecture. Last piece. How do you walk an interviewer through this in 45 minutes? That is next. The 5-phase interview framework. Phase 1 requirements. You must state upfront that network timeouts will happen and the system must handle them gracefully. Phase 2 estimates. Calculate how large your Kafka queues need to be to buffer transactions if the NPCI switch goes down for 30 minutes. Phase 3 high-level design. Draw the message queue separating the fast API from the slow workers. Draw the state machine. Phase 4 deep dives. Explain how a nightly reconciliation job catches transactions where the webhook was dropped by the network. Phase 5 trade-offs. This is where you shine. Explain exactly why you chose an asynchronous flow over a simple synchronous API, proving you understand scale. Before this video, a payment was just a synchronous REST call. After this video, you know that robust payments are asynchronous state machines driven by message queues and webhooks. Every engineer who designs this flow from memory is a senior engineer in the room, regardless of their title. AI writes the code, you design the system that survives the network trap. In the next episode, we double click on transaction idempotency. If a user double taps the pay button during a lag spike, why aren't they charged twice? We will learn how to design the log that prevents it. Subscribe to ByteLearn for the complete PhonePe system design survival series. Hit the bell. Question: what is the most dangerous state in the payment state machine? Let me know below.